Okay, good morning, everyone.
Good
So,
morning, sir.
good morning. So, till now, we have discussed about the mathematical model formulation, where we have seen how to develop the objective function, how to write the constraints. So, depending on those objective functions, we actually target not to only develop the mathematical model, but also we are targeting to develop the solution for that particular case study that has been given to us. So, as a part of this thing, we would be dealing with the solution of these case studies. So basically, if you remember, I have told you before, I guess, one or two lectures that there are multiple methods that we would be dealing with. Out of those, today we would be starting with the first method, that is the graphical method. And for that only, I have asked you all to keep a scale and pencil with you. I hope everybody would be having the scale and pencil with them so that you can just take a note of whatever I am doing and whatever I am teaching. Okay, now there are some of the classical mathematical methods that you have already learned for development of the solution. The first one was to solve the linear equations that you have already learned how to solve the set of the linear equations and to find the solution for all those linear equations. The second one was you learned, I guess, probably you have learned the Gauss-Jordan method and Gauss elimination method. So that was the another method that you would have learned to find the solution of the different linear equations or set of the linear equations. Now, this mathematical model, we know that it is working, but how this particular set of the linear equations are giving us the solution, what is the interpretation for getting that particular solution, we haven't learned it. In our mathematics subjects, we haven't learned how we can get the solution for this particular set of the equations. We have learned that, okay, multiply with the coefficients of the variables and then subtract it, and we would be getting the elimination of one of the variable, and the another variable we would be solving it, and after that thing we would be having the solution for one variable. Put that particular value into one of the equations and you would be getting the solution for the another variable. Yes, definitely we have learned this thing, but what is the interpretation of these all things? So that is the thing, but we would be learning that particular examples, using the particular examples by solving the set of the linear equations in the graphical format by using the graphical method. So for that, let me just share the screen with you all. I hope the whiteboard screen will be visible. Okay, so let me just paste the graph over here. I will just paste the graph axis over here. In the usual course of the lectures, I would be preferring that you can have the graphs with you. But since there is the online mode, I won't be suggesting you all to purchase the graphs from the stationaries. I won't be forcefully telling you this thing. But if you are having the graph, then you can practice it in the graph paper only. Else, I would be saying that you can make this type of structure in your notebook, but make sure that whatever structures you are making are correct as far as the unit length is concerned. So make the proper length in between the two units. For example, if you are having 1 centimeter length in between these two units, then also you would be having 1 centimeter length in all the rows. And same thing, if you are having 1 centimeter in the column, then you should be having the 1 centimeter in all the columns. So that utmost care you should be taking, because if you are missing onto that particular unit matching, then you will be having the wrong answer. So if I tell what I have told in the very first lecture, that if you would be making any of the small mistake, then can have the wrong answer. And if you are doing the things clearly, then there is no chance of making the mistakes until and unless you are making some minute mistake or silly mistakes while doing the calculations. Otherwise, you will be definitely getting the full marks for each and every questions that we will be doing in this particular subject. Okay, so this is nothing but our x-axis, there is nothing but our y-axis. Let's directly start with the equation. Let's take the equation x plus y is equals to 5. Let's take this particular equation x plus y is equals to 5. So this is nothing but it is the linear equation. Linear equation. Why? Because the degree of polynomial is equals to 1. This is my polynomial and the degree of polynomial is equals to 1. That is the reason it is a linear equation. How can I draw the line? So how many points, how many minimum number of points I would be having to draw a line? Can anybody tell me how many minimum number of points I would be requiring?
2.
2. Correct. Right. So the minimum number of points you will be requiring is 2. So for getting the perfect architecture of this line, what I should be doing, can anybody just have the suggestion for this thing? What I should be doing?
Sir, assume x to be 0 and evaluate y as 5, and likewise put x as 1, 2, 3.
Okay, fine. So that is one of the solution. Put x is equals to 0, so we will be getting y equal to 5. So that means my x comma y point will be 0 comma 5. This will be my 1 point. Else put y equal to 0 and x is equals to 5. So x comma y will be equal to 5 comma 0. We have got 2 points. And we know that from the 2 points, we can easily draw the line because this is the minimum number of points that I require to draw a straight line. So let's plot this thing 0 comma 5. 0 on the x-axis, 5 on the y-axis. So this is the point. 5 comma 0. 5 on the x-axis, 0 on the y-axis. So this is the point. Now take the scale and now adjust it. Let me just adjust it. And you can draw the line. This is the particular line which I am drawing. So I have got the line, which is nothing but x plus y is equals to 5. This particular line, if I say it's the line which is nothing but x plus y equal to 5. This is what we all know. I guess this should be clear. This is the point. Just give the points. This is the point 0 comma 5. This is the point 5 comma 0. Now we have seen in our all the mathematical models that it is nothing but x plus y greater or equal to 5. We have developed this type of the equations, right? In this mathematical model development, we have developed this type of the equations, x plus y greater or equal to 5 or x plus y less or equal to 5. This type of the equations we have developed. So how can I represent this type of inequality? This is nothing but equality. This is the equality sign. But in case of our mathematical modeling, in case of the constraint discussions, we are having this inequality. So can anybody just provide the suggestion? How can I ensure this inequality? How can I ensure this inequality?
Yes, sir. For x plus y greater than or equal to 0, above the x plus y equal to 5 line region.
Correct.
And
Right.
for x plus y less or equal to 5 below the region.
Correct. So that is the correct answer. See, over here, we have been given x plus y equal to 5. So this particular line which we have drawn is splitting this entire region into two parts. Let's say part number 1 and part number 3. And this line itself is the second region. Consider this line is the second region. This one is the entire region which is below this particular line. And this 3 is the entire region which is above this particular line. I am excluding the points which are here on the line. I am not considering the points which are on the line in either region 1 or region 3, but I am giving it as the separate region as region number 2. I am giving it as the separate region, that is region number 2. So this entire graph is the collection of the region 1, 2 and 3. The entire graph is the collection of the region 1, 2 and 3. So if I can just write over here, the entire graph is the collection of region 1 plus 2 plus 3, the 3 regions. Now, if I am having the equality is, let's say I am having x plus y and star 5. Now this star is nothing but the sign of the equality or inequality. So I would be having star and region. I would be just writing this thing, star and region. So let me just move the scale. Okay. So let's say my star is equals to, is the sign equal to, then my region 2 will be there. That is x plus y equal to 5. This is my equation, x plus y star 5. Let's say my star value is less. That means it will be x plus y less than 5. So it will be region number 1. Let's say my star value is greater than, that is x plus y greater than 5. Then it will be region number 3. Let's say my star value is less or equal to, that means x plus y less or equal to 5. So it will be region 1 and 2 combined. Why? Because less is 1 and equal to is 2. So 1 and 2 combined. And let's say my equation or star is having greater or equal to. So equation will be x plus y greater or equal to 5. So my region 2 and 3 will be combined. So this is what you need to understand for development of the graphical structure of the equations or the graphical modeling for the entire mathematical model that has been generated or obtained or formulated. So these are the 3 regions. The entire graph is been divided into 3 regions, 1, 2 and 3, where region number 2 is the line itself, region number 1 is below the line, and region number 3 is above the line. And these are nothing but my set of the inequalities or equality. So anybody having any doubt in this particular example? Is this thing clear? Anybody having any doubt? Okay, Viraj is to say, can we include not equal? Good one. Yes, definitely we can include not equal to sign. But since I have not, why I have not included not equal to sign, the reason for not including not equal to sign is that in our mathematical model, we usually don't deal with not equal to. So that is the reason I am not including that thing. But if you want to include not equal to just for the understanding, then it will be the region 1 and 3. It will be the region 1 and 3. Why? Because it will be saying that, okay, x plus y not equal to 5. So that will be the region 1 and 3. Because at any of the point, if you take the values at any of the point, for example, if I'm taking this point on this line, if I taking this point on this line, then it will be the x value will be equal to 2. If you can just extend it over here, x equals to 2, x equals to y equal to 3. So this is my y, this is my x. So over here, x plus y will be equal to 5. But we want x plus y not equal to 5. So you take any of the point except this particular line will be giving you x plus y not equal to 5. So just take this particular point. So it will be nothing but it's above this line. So it's 3 and 3. So that's 6 and it's not equal to 5. Okay. But in the development of the mathematical model, we usually don't take not equal to sign. We are dealing with these 5 constraints only. Specifically, we are even not dealing with these 2 constraints as a part of our course. But I will be also telling you some specificity for these 2 constraints also. But we will be doing the practice for all these 5 constraints except this 6th one. Okay, so if you are not having any doubt, then I will be moving to the another example. So let me just erase this particular example. And let me just take one real example directly of some mathematical model. Just let me write some mathematical model, random mathematical model, and then we would be solving the questions that we have already done. Let's say the mathematical model that we can develop is the maximization process, 15x1 plus 10x2. Now in this particular example, I will be explaining few of the terminologies. But before that, I will be drawing some lines for this thing. 3x1 less or equal to, let's say 180, 5x2 less or equal to 200, and x1, x2 greater or equal to 0. Let's say this is my mathematical model that I want to draw. This is the mathematical model that I want to draw. This is the objective function. The objective function is the maximization. 4x1 plus 6x2 less or equal to 360. This is my first constraint. This is my constraint number 1. 3x1 less or equal to 180. This is my second constraint. This is my second constraint. Let me just highlight it using some another color. And 5x2 less or equal to 200 is my third constraint. And x1 comma x2 greater or equal to 0, that is the non-negative constraint. So we are always dealing in the positive reduction of x1 and x2. Fine. So let's say this all the three lines plotted over here. So first of all, forget about the conjunction of all these three lines. Forget about all the inequalities and try to convert it into the equality. So if you are given this one, this is the first constraint that we are being given. So this is less or equal to inequality. As of now, while drawing the line, just forget about the inequality and convert to the equality, equal to sign. Just for the sake of converting or drawing the particular line, we are converting it into the equal to sign. So just put x1 is equals to 0. So we will be getting x2 value. So if we are putting x1 equal to 0, so 6x2 equal to 360. So it will be 60. So our point will be 0, 60. Put x2 is equals to 0. So this will be 0 and 4x1 is equals to 360. So x1 will be equal to 90. So my point will be 90, 0. So this is my x1. This is my x2. Now, since I have just taken this graph from the internet, just to show you in more better way, I would be scaling this thing as 1 centimeter is equals to 10 units. I would be scaling up this thing as 1 centimeter equal to 10 units. So the same thing like you used to do in your schooling days, I probably guess that you have done this type of things in the graph also, and probably in one or two subjects in the engineering career also. Fine. So this is x1. So if I just write over here, it's nothing but instead of 1, I would be having 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. For x2, I will be having 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Now, I will be simply noting down this point. So I would consider the first constraint in blue. So I will be just drawing the things with blue for the first line. So it's 0, 60, 0, 60. So over here. And 90, 0. So it's over here. So I will be drawing the line for this particular points, because to draw the line we require 2 points. So let me just draw the line. It's quite difficult to have this ruler adjusted every time. So probably you will be having quite speedy answer than me. Okay, this is the first constraint that I have drawn. Now second constraint is 3x1 less or equal to 180. So I will be converting it into the equality sign. It's 3x1 equal to 180. So x1 will be equal to 60. So that is nothing but what type of the line I would be having. I don't have x2. So what type of the line I would be having? Can anybody just suggest?
Sir, vertical.
Right, it will be vertical line. So let me just make my scale vertical, and it will be x1 is equals to 60. I will be drawing the line over here. I will be drawing with green. Why? Because the second constraint I will just assume to be drawing in the green. And the third constraint is nothing but 5x2 less or equal to 200. So I'll be converting it into the equality sign equal to 200. So x2 is equals to 40. So it will be the horizontal line. So let me just convert the scale to the horizontal, and it will be equal to 40. So let me just put over here this, and I will be drawing it with pink. So I have drawn all the regions. I have drawn all the three lines. I have drawn all the three lines. This is my third constraint and this is my second constraint. Now I will be considering for drawing this all the three lines, I have considered instead of inequality, I have considered just the equality sign. Now I will be including the inequality. So for the first case, if my equation is less or equal to, for the first case, if my equation is less or equal to, so that means I will be considering the entire below region. Let me just take this particular line only or blue color only. So I will be having all this entire region. So just focus over here for 2 to 3 minutes, everybody. So what I have done, this is nothing but less or equal to. So the entire region which is below this particular line, including this line, I am saying the entire below region, including this line, is my first constraint. Now the second constraint is less or equal to 180. So okay, so sorry for the interruption. I just got to one call, so that was the reason. Fine. Now, the second case is nothing but 3x1 less or equal to 180. So that is the vertical line that we have drawn, the green one, the vertical line, it's the less or equal to, less or equal to. So for this particular case, the less or equal to will be the entire region on the left side. So if you are seeing the less or equal to sign, so it will be the entire region on the left side with this line. So let me just draw less or equal to this entire region with green. And the third constraint is 5x2 less or equal to 200. 5x2 less or equal to 200. So for this particular case, I have considered pink color and the entire region below this pink line. So the entire region below this pink line will be there. So I will simply shaded the region. I will simply shaded the region. Now can anybody just tell me what could be my region which will be satisfying all the three conditions? What will be my region that will be satisfying all the three conditions? I can't say this particular region. If you are just saying, I can't say this particular region. I can't say this particular region. Whatever I have drawn with the blue highlight, I can't say that particular region. Why? Because it's not satisfying all the three conditions. So what will be my region that will be satisfying all the three conditions?
So the triangle forming between 2, 1 and 3, 120.
Right. So if I can just draw the line, it will be something. It's basically we have been also been given x1, x2 greater or equal to 0. So all the values above this line and all the values on the right side of this line. So that also we need to consider. So if I just draw the shape, so it will be something which I will be drawing in the black. So just point me out if I am going wrong in this particular drawing. So this is the particular thing that will be my region that will be satisfying all these constraints. So if I can just highlight using this gray color, so probably it will be looking quite dull for this graph, but I hope that will be quite explain you what we are trying to do. Fine. So that means this is the particular region which I have drawn in the black is my region which is intersecting all these three conditions, and this particular region is called as the feasible region. This particular region is called as the feasible region. Feasible region, why? Because it is having the satisfaction of all the three constraints. It is having the satisfaction of all the three constraints. That is the reason it is called as the feasible region. Now, since this is the closed region, it is also called as the bounded region. It is also called as the bounded region. I won't be putting or in between these two things, but I will be putting plus in between these two things. It is also called the bounded region. Why? Because this is bounded on all the sides. If you can see, I am having the closed structure. It is not open from all the sides. I have bounded it from all the sides. If just imagine, just to give you the example, if my this condition won't be there, that is x1, x2 greater or equal to 0. So that means I won't be bounding it from bottom. I won't be bounding it from bottom. So that would be my feasible region plus unbounded region, because I am not considering this black lines that I have drawn on the axis. So that is the reason I would be saying that, okay, I am not bounding my particular feasible region from the bottom side, and that is the region. That is the reason it is termed as the unbounded region. Okay. Now, as a part of the solution, I will be finding the corner points. So let me just erase this thing. I will be having another terminology. So in this particular question, I will be exposing you with all the terminologies that are dealing with the mathematical model stuff, that are dealing with the graph method. So the next terminology is corner point. Corner points. So the corner points are this, all the points. If I can just show, if I can just draw with the green. So these are all the corner points which are lying in the corner of the region. These are all the corner points. These are lying on the corner of the region. The corner points are there which are lying on the corner of all the regions. So what will be the value for this particular point? Can anybody tell me what could be the value for this particular point? What is the coordinate for this particular point? For the point number, let's say 1. Okay, 0, 40, 30, 40. So it will be 0, 40. This will be 0, 0. This will be 60, 0. This will be 20 and 60. So 60, comma 20. I have drawn it quite in the bad manner with all these things overlapped. So it may not be clearly visible, but this point, if can anybody point out to me?
30, 40.
Okay, it's 30 and 40. So how can we get all these points? How can we get the intersection of all these points or the all these points? So for that, if I can just provide you some more in more better format, let me just erase all these things. Let me just erase all these things, or let me just draw the graph so that it provides more clarity to everyone. This is the first example, so that is the reason we are dealing in more detailed format. So for the first equation, what was our point that we have just discussed? It was x to be equal to 0, x1 to be equal to 0, x2 was 60, and x2 to be equal to 0 over x1 was 90. So it was 90 comma 0, this one, and 0 comma 60, so this one. So I will be drawing the line again. So this is again the revision for those who didn't understood it. Okay, let me draw the line. So this is the first constraint. Second constraint is x1 is equals to 60. X1 is equals to 60. So let me just convert to the vertical scale. X1 to be equal to 60. So this particular will be drawn with the green. And x2 is equals to 40. Okay, x2 is equals to 40. Okay, so these are all the this is the region which you will be considering, keeping in mind x1 comma x2 is greater or equal to 0. So now I won't be highlighting this particular region. So which are the points that are considered as the corner point? So if I can just draw the boundary line for the entire feasible region, then this is my entire feasible region. So this is my first point, which is nothing but 0, 40. How I have obtained it? So it's directly lying on the axis. Now this is my origin 0, 0. This is my point which is lying on the vertical axis, that is 60, 0. This is the point which I need to find out. So there are two methods. So I won't be directly saying that you just look over the coordinates over here, because that was the reason. If you remember, I told that the centering should be perfect. The distance between the two lines should be equal. it should be equidistant for all the lines. If you won't be drawing the equidistant, then there are the chances that this particular distance may vary and you can get the wrong answer. So in order to prevent those particular trap, what I need to do, just solve the two lines. This particular point is obtained by the intersection of the green and the blue line. So you can see the green and the blue line, the intersection of the green and the blue line will be giving you this point. So what is the green line? It's x1 is equals to 60, that is the green line. And the blue line is nothing but 4x1 plus 6x2 is equals to 360. So just substitute over here. So it's 240. It will be 120. X2 is equals to 20. So that is nothing but x2 is equals to 20 and 60 comma 20. It will be our point. So although you can just compare it over here, it's 60 comma 20. So that means our equation is correct. So don't just only verify from this coordinates. This is the Cartesian coordinates. So don't verify from that, because there are the chances that you may make the mistakes while drawing the axis, and that will be leading you to the wrong calculations. So just try to solve these equations and then try to locate the point. Same thing over here. If you can just see over here, this particular point is the intersection point. Now, with the reference of this point, this is the intersection point of the pink line and the blue line. So pink line is nothing but x2 is equals to 40, and the blue line is 4x1 plus 6x2 equal to 360. So just put x2 over here. It will be 6 into 240, so 120. X1 equal to 120 divided by 4, so x1 is equals to 30. X1 is equals to 30. Now, this is the mistake that I have made intentionally, because see, if you can just see, I have shifted this blue line somewhat above. Then where I should be keeping. This was the intentional mistake that I did, just to make you realize that how wrong you can go. If I would have just seen the coordinates, then it will be pertaining to this particular thing, that is 35. So I could have written 35 comma 40, which is not the correct thing. Why? Because of the shifting of this particular blue line, a minute top shifting. Instead of these points passing through these points, I have shifted up just a little bit. And that little bit shifting has resulted me in the difference of 5 units of x1. So that is the reason I won't be directly checking for this particular thing. Rather, I would be taking 30 comma 40. That is my point of intersection of these two lines. Now I have received 5 points. That is nothing but first is 0 comma 40, 0 comma 0, 60 comma 0, 60 comma 20, and 30 comma 40. These are all the 5 points which are termed as the corner points. They are all termed as the corner points. They are all termed as the corner points. Now, my next step will be to look into the objective function, that is to maximize 15x1 plus 10x2. This is my next step, to maximize the objective function. So what I will be doing for all the corner points, I will be finding the corner point solution. Corner point solution. For all these corner points, I will be finding corner point solution. So how I will be finding? So just substitute 0 comma 40 into this one. So it will be 0 comma 40. So x1 equal to 0, x2 equal to 40. So it will be 400. 0 comma 0. So it will be 0. 60 comma 0. So it will be 15 into 60. It will be 900 plus 0. So it will be 900. 60 comma 20. So 15 multiplied by 60. So it will be, what will be the answer? 15 multiplied by 60 plus 10 multiplied by 20. So this is 200. It's 900. So it will be 1100. Point out to me if I am going in the wrong calculation. And 30 comma 40. So it's nothing but 15 multiplied by 30 plus 10 multiplied by 40. So this is 450 plus 400. It's 850. This is 850. So all these answers are my corner point solutions. Corner point solutions because I obtained the solution pertaining to these corner points. And they are lying in the feasible region. This is the entire feasible region. This is my feasible region. The region which I have shown with the gray highlighter. The region bounded by this particular field, black line. So they are nothing but my feasible region. Since they are the points that are lying in the feasible region, these points along with the corner points, they are also called as the feasible points. They are also called as the feasible points. These solutions are also called as the feasible solutions. Now, my main intention is to maximize this particular output. So what is the maximum value? This is the maximum value. This is the maximum value. So this particular answer, which is the maximum value, it is called as the optimal solution. That is what our intention is. Optimal solution. Optimal solution. Now, just for an instance, just look in the graph. Just look into this particular graph, just for the instance. If I'm taking this particular point, if I'm taking this particular point that is highlighted in green, that is nothing but 20, 20. I'm taking this particular point that is 20, 20. This particular 20, 20 is not lying in the corner, is not lying in the corner of this particular feasible region. So it is not termed as the corner point. It is not termed as the corner point. But it is lying within the feasible region, so it is also called as the feasible point. It is also called as the feasible point. What are the feasible points? The points which are satisfying all the constraints are called as the feasible points. So this 20, 20 is also termed as the feasible point. The solution corresponding to this 20, 20, that is 300 plus 200, so it will be 500. It is called as the feasible solution. It is also called as the feasible solution. But remember this thing, they are not the corner point solutions or the corner points, but they are only the feasible point and the feasible solutions. So whatever solution you are obtaining pertaining to the corner points are called as the corner point solutions. And out of all the solutions that you have obtained, whatever solution you are getting as the maximum value will be called as the optimal solution, because out of all these things, 1100 is the maximum. So this is the optimal solution. So this is nothing but our method solved by the graph, and thereby it is called as the graphical method. Graphical method. Any doubt in this particular question? Anybody having any doubt? Just point out to me if you are having any doubt. Anybody? I want the acknowledgement from everyone. I have received acknowledgement from 15 people. I am waiting for others also. Is it easy? Okay. Karan was asking, sir, is it possible that we may get best optimal solution inside feasible region but not at corner points? Okay. It is a very good question. This is a really good question from Karan, and I would be liking to give him one bonus mark The same thing which I did in the previous semester also. You may not know that I was noting down the bonus points. I also told a couple of the times, but I will be giving the one bonus mark for this really good question. So what his question is it possible that we may get best optimal solution inside the feasible region, but not at corner points? Okay, so anybody who can give the answer to this question will be getting one more bonus mark. So Karan has already got the bonus mark for this really good question. But if anybody want to attempt for the solution and if it is found to be viable, then you will be also getting one more bonus mark. Okay, Akshat is to ask that if we have unbounded region, then also we will consider corner points. Yes, we will be considering the corner points. We will be taking the unbounded region also, but for the case of the unbounded region, generally we won't be having the maximization problem. It will be the minimization problem. It will be depending on the scenario that how we can have the unbounded region. So we will be also taking the unbounded region for that particular case. Okay, the same question, Prerna has asked that if the feasible region is not bounded, then okay. So after answering this question that is asked by Karan, I will be switching to this particular example because I guess three people have asked the same question. What if the feasible region is not bounded? Then okay, anybody who want to give the answer to the question of Karan?
Sir,
Yes.
sir, what I think is when we are bounding the region, so they are the maximum points that we are taking in. So all the points in that region will be the lower from the boundary point. I mean, the corner points. So I think we will not getting the more than that. I mean,
Correct.
from the
Correct. Your understanding is correct. So I will be giving you one mark for this particular answer. Your understanding is correct. But in terms of the technical aspects, I will be looking into some another uh, solutions also. Okay. Viraj, the same answer like Prerna, Akshat also will always get optimal value at the corner points as they are the maximum possible points. Fine. Okay, so in terms of the technical aspects of this particular optimization technique, the subject, let's say if you are taking any point over here, let me just draw the point in the blue. If you are taking any point on the here, now if you are just moving on the right side of this particular point, now this blue is not a corner point. Now if you are moving on the particular right side at some distance delta, then now your new point will be this one. Your new point will be the next one. So if I can just say this was my original point, I have moved right side by some distance, small distance delta, so it will be now shifted to this particular point. Now the area, the word area is really important over here. The area bounded by this particular point, the initial point, was this much. If you can just see, the area bounded by this particular point was this much in terms of the feasible region. Now we are moving to the right side. That is the reason my area is increased by this factor. My area bounding has increased by this factor. Now on further moving to the right side, my area bounding by that particular point will be also moving or will be also increasing by that factor. So that is the reason I will be selecting the region which is having the highest area coverage, and higher the area covering, my answer will be more and more better. Higher the area covering, my answer will be more and more good, or my answer will be more and more optimal. That is the reason I will be considering the corner points, because by considering the corner points, I don't have any chance to move into the further left or the right side as far as the cases are concerned. So if you are considering this corner point 60, 20, so you cannot move further this side, because then it will be the infeasible region. So that is the answer for this particular question, that if you are having the point which is not the corner point, then by moving delta amount on the either of the side, which will be giving you the higher area coverage, will be giving you more optimal solution. So this would be your answer. Okay. The next question that was being asked is by Viraj, that what if we get all the same corner points? Fine. So for the case for this corner points, if you are having multiple values that are the same, then you can have the multiple answers. You can have multiple answers. So that is not an issue. You can have multiple answers. Okay. Now, giving the answer for one of the question, I guess it was asked by three people, who is saying that what if my feasible region is unbounded? Okay, so for that, I won't be taking any of the mathematical model example, but let me just directly take some random lines. If I am having this particular line, and if I am having this particular sum line, I don't know the equation of the lines, but just assume it to be this one. If this is the case, let's say this particular line is equation number 1, or and this particular line is equation number 2, and I am given that okay, equation number 1 is having greater or equal to inequality, equation 2 is also having greater or equal to inequality. So that means my feasible region will be the entire region which is described by this particular line from here to here, and it's basically also we have been given x comma y greater or equal to 0. That means our entire top region will be there, this particular region will be there. Now this is the feasible region. You can see this is the feasible region, plus it is unbounded. This is the feasible region plus it is unbounded. So over here, the objective function that you will be dealing with won't be maximization function, because if you are considering the maximization function, then if you are taking any of the point over here, let's say if you are taking this particular point, then by moving into the top direction, you will be always getting more and more better answer. So it won't be the maximization problem. Instead, it will be the minimization problem. Instead, it will be the minimization problem. So for the minimization problem, you try to find the minimum value. You try to find the minimum value. So depending on the feasible regions, depending on the boundedness of the regions, your optimization function or the objective function will have maximization or minimization cases. So if you are having this type of the functions that are being there, then it means that you won't be having the maximization objective function, but instead of that, you will be having the minimization objective function, this particular case. So if you are considering the minimization objective function, then let's say you will be having over here, if you are considering the point, over here if you are considering the point, and over here, suppose if you are considering the point, let's say there you are considering these 3 points. Now you can claim that this point can be anywhere else. You can claim that this point can be anywhere else. Then in that particular case, because see, this is the extended line, it is the unbounded. So in that case, you can also need to write in your solution that, okay, if you are moving on the right side with the delta amount, then your objective value will be increasing. Your objective value will be increasing. So you are forced to move on the left side only. How much you can move on the left side? You can move till this point. If you are having this particular point, then you can move on the further downward side to reduce your optimal value. So how much you can move? Let's say you can move till this point. So that means this will be your feasible solution. So I hope this particular reason would be quite clear to those who have asked the questions, and to everybody. If my region is feasible and unbounded, then what will be the cases? Then this will be the cases that your objective function won't be the maximization, it will be the minimization. Because if you are further moving on the right side or the top side, your values are going to get increased and the objective values are going to get increased, but you are moving in the opposite to what you are expected to do. So that is the reason you will be having more value instead of lesser. So that's it from today's session. I would be suggesting that you can just try at your home first and the second example that we did. The first and the second example that we did, you can try it at home and you can try to find the solution for the answers that we have done for the first and the second mathematical module formulation examples. We will be starting from tomorrow the third question onwards, and we will be developing the practice for the third, fourth, and fifth, and so on, the questions. You can just try it at home for the first and the second question. So that's it. You can just write your roll number and name for the attendance. And if you are having any doubt, then you can ask me and you can join for the next session. Thank you, everyone.
Hello, sir.
Yes.
Sir, can you share the screen again?
Yes. Okay.
Sir, here you mentioned the above the part. If another equation will become in below part and above part, both will become in the region.
Right. So suppose you are having some
So,
another line. Let's say suppose you are having this line, particular line, and that is the equation which is
no,
dealing with less or equal to.
no, sir, not. I am not telling about this. Uh, below region, sir. Let me draw. Sir, here.
Okay.
Yes, sir, this portion will be also coming, and this portion also will be coming. So, which condition, minimum or maximum, will be occur?
Okay. So if you are having these two lines, let's say in the first and the second line, this line and this line, if you are having these two lines, okay. So you are trying to say that this first equation will be there, then over here the line will be there, and this particular line will be there. Like that, you are trying to say?
No, sir, no, sir, I am not. Yeah, in the graph, you are drawn this. Sir, just a minute, sir. This portion will be coming, and this portion also will be coming
Okay.
in region.
The bottom portion will come only
Yes,
if you are not having this first equation. If you are having this first equation with greater or equal to sign, so you won't be able to have this bottom portion, because the portion will be only having the top portions only, because it is the greater than sign.
yes, yes, sir, yes.
Okay, so I just got another case study which I will be discussing in tomorrow's session also. from the question that you asked. So I will be discussing that case study also.
Okay. Thank you.
Okay.